This video is designed as a crash course for any student that missed naming ionic compounds. We will be going through the naming of some basic compounds that have two elements called binary ionic compounds, and then we'll be doing polyatomic ions, and lastly we'll be going through the transition metals and tin and lead. Real fast, we'll hit through the notes here. The International Union of Pure and Applied Chemists is who develops the international rules on these, and we already have a basic understanding of how the formulas work. Like in C8H18, we have an idea that there are 8 carbon atoms and 18 hydrogen atoms, and we've learned how to draw structural formulas and Lewis structures of those. Ionic compounds like this, what we will learn to call aluminum sulfate, we understand that there's 2 aluminum atoms, and there are 3 sulfates, and SO4 is a polyatomic ion called sulfate, so there's 3 of those. Each of those sulfates equates out to a sulfur and 4 oxygen atoms then bonded to it. So that there's a grand total then, you can distribute this 3 through here, since there are 3 sulfates, there are a total of 3 sulfur atoms, as you can see by the green spheres, and if you distribute the 3 into the parentheses, 3 times 4 is a total of 12 oxygens, and each of the greens have 4 oxygens, so 4, 8, 12. And so we have our basis of the formula. Ionic compounds are named in a pattern where it's always the cation followed by the anion. The cations, again, are usually the positively charged metals. There's some exceptions to those, like hydrogen and some polyatomic ions. The anions are negatively charged and are usually nonmetals. Naming of the cations is pretty simple. It's just the name of the element. So the calcium ion, if you remember how to get your charges from the periodic table, family 1 here is a charge of positive 1, except for hydrogen. Hydrogen could be a +1 or a -1. And the alkaline earth metals, group 2, they're usually a +2 charge. I think they're always a +2 charge. We'll skip over the transition metals, and group 13 is generally a +3, and group 14 is generally a ±4, and group 15 is a -3, and the oxygen family, group 16, is a -2. The halogens, group 17, are a -1, and of course the the noble gases are 0 because they don't take part in the bonding. So the cations are just named after the elements. So you look up calcium on the periodic table, and on the periodic table, calcium is in this family, so it's a +2 ion. You can write that several different ways. I generally prefer the form of Ca +2. A lot of chemistry books, they use the convention of 2+. I'm not sure the history of that, but to me that's kind of archaic in nature, but maybe there was a reason for it. And I've seen different textbooks use the double plus for calcium, Ca++. But either way, they're all called calcium. So potassium, likewise, potassium would be called up. Here's potassium. It's in the +1 family, and it was just potassium with a plus. Notice there's no 1, because in chemistry you just generally ignore the 1. You already got the potassium ion there. You've already got the charge plus, so you don't have to write the 1. If you look up aluminum, it's over here in group 13. Here's aluminum right here, atomic number 13. In group 13, it's a +3, and so you could write that as aluminum +3, how I generally write it. Conventionally, textbooks will use aluminum 3+. I've never seen anything written like the calcium version here is a +++. So notice how those oxidations are superscripts. Anions, on the other hand, they're named using an "ide" system. What you usually do is you drop the last syllable, sometimes the last 2, and you add an IDE suffix. So fluorine becomes a -1 ion and is now called fluoride, and chlorine is chloride, and oxygen is oxide, sulfur, sulfide, nitrogen, nitride, and phosphorus, phosphide, etc. And so the ones on the periodic table that generally do that, silicon could be silicide, carbon could be carbide, germanium wouldn't do that. Arsenic would be arsenide, selenium would be selenide, tellurium, telluride, iodine, iodide, bromide, chloride, fluoride. If astatine does it, it would probably be astatide, although I don't think you'll ever see that. Antimony usually doesn't form an anion. It's usually, I think, a positive ion. Same with germanium and tin and lead. And so you got the stair-step metalloids here. You see this little break here. I'm not sure about boron either. Maybe boron could be boride if it forms any kind of a negative ion. I'm not sure. So there's your idea. You just take the name of the element, drop the last two syllables, or usually the last one, and stick an IDE on there. So if we are naming things, naming is pretty simple. So here's a couple of samples from the notes. NaCl would be sodium chloride. SRF2, strontium fluoride, and all you're doing is taking the metal name, combining it with the anion name, and that's how you generally get your name. Formula writing is a little bit more difficult. We have to get charges off of the periodic table. On this slide, I will animate and show you what's going on there on the naming of these. And so let me bring this a little bit more into focus here. If we're writing the formula for rubidium sulfide, the first thing we want to do is get our symbols and translate it from words into symbol form. So the symbol for rubidium is Rb, and the symbol for sulfide is S. Next, we want to get our oxidation numbers from the periodic table. And so rubidium is over here in the alkali metals. It's a +1, and sulfur is over here, and it would conventionally be a -2. And I write those above the elements as you're first learning how to write those. Step 3 is you ignore the signs, and you do what I call a crisscross. And what happens on the crisscross is you have the 1 and the 2, you ignore the signs here, so I've gotten rid of the signs, and you literally crisscross them like this. And so the 2 goes behind there, and the 1 kind of went a little bit distant, but it goes behind the sulfur right there. Step 4, we're cleaning some things up. You ignore any 1s because just having this, the symbol there is indicative that you have 1 of those atoms. And the idea of the crisscross is that a quick way, all ionic compounds should add up to a total charge of 0. And so if you look at this, I have 2 rubidium atoms and a sulfur. Well, the 2 rubidium atoms, rubidium has a charge of +1, and there's 2 of them. So the total charge from all the rubidium is +2. 2 rubidium atoms is +2. The 1 sulfur atom has a -2 charge. And so if we add those up, we have a total +2 from the rubidium and a -2 from the sulfur. +2 minus 2 equals up to 0. And that's the idea right there, is you got a total net charge of 0 on these. Crisscrossing is usually the quick way in order to do that. I do have a note here. It says and reduce. Sometimes we get subscripts, like if this is a 2 and a 4, those would be reduced then. You divide everything by 2, and so it would be a 1 and a 2. And we'll see those here in the examples here as we go through these. All right? Okay, let's take a look at some samples of these. And these come from the first page of the note packet. If you don't have it, you can download it from the website in various ways that we have at Milton Union to do that. NABR, I'll just be typing these in here. If you have NABR, it's just a matter of translating it into sodium bromide. Very simple process there. MgCl2, Mg is magnesium, and Cl2 is just simply chloride. Notice how the numbers don't do anything to us. They're later on, the numbers there, the subscripts will tell us something, but in ionic naming, that's not the case. So a lot of people want to name this magnesium dichloride. That's not the correct way to do it in ionic terms. It's just simply magnesium chloride. Na2O, name of Na is, I just about typed natrium, its Latin name, sodium oxide. And Al2O would be aluminum oxide. So naming, pretty simple. Formula writing, generally a little bit more complicated. We'll be doing the crisscrosses and all that good stuff here. So we'll start here with potassium bromide, and I have a K, and bromide is a Br. Getting my bearings here. Potassium is a +1, and bromine is a -1. And there's no need to crisscross because +1, -1 already balance off. So simply the formula is KBr. And I didn't mean to mark a line through that, so we're just going to undo that. So KBr is our formula for that one. Next one, I'll write this over here so I got some room, is barium. So that's Ba. Silicide, and I give myself some space because I know there's probably going to be some numbers written in here. I will go down here and we'll look up the charges from barium silicide on the periodic table. And barium is in family 2, and so that's the +2 ions. And silicide is in the plus or minus 4. So then I always ask, well, which version is it? It's the plus 4 or is it the minus 4? Well, since silicide is written last and it ends in IDE, that's your indicator that it's the anion version of silicon. And so the anion version would be minus 4. And the barium was a plus 2. Next step is we're going to ignore the signs and we're going to crisscross. So we put a 4 here, we put a 2 here. Now's when we have this cleanup step. I've got a 4 and a 2. Those are reducible. So I'm going to divide everything by 2 and rewrite them. So I'm going to get rid of the 4 and divide it by 2. I'm going to write a 2 there, and 2 divided by 2 is 1. So we'll go back to pen tool here. And so this was a 4, and so I divided it by 2, that's 2. This was a 2, and that now becomes a 1, which I'm not going to write because you don't write the 1s on here, because just having SI is enough. So now if you want to go back and make sure that the charges are right after that reduction step, you can just simply multiply everything by the charges. I have one silicon atom. It's got a minus 4 charge, so the total charge from silicon is negative 4. Everything has to add up to 0. I have 2 barium atoms with a plus 2 charge, so 2 times 2 is plus, I wrote a plus 2, that's totally not right, it's a plus 4. And so we have a plus 4 here, positive 4, that's supposed to be a 4. So we have plus 4 and we have minus 4, and so we have a grand total, here we go, we have a grand total of it adding up to 0, plus 4, minus 4. All right? Reduction step is just because ionic compounds, if my students remember, they form these giant crystal lattices, and so you reduce them to what's called that formula unit. What's the smallest ratio of all the atoms? And so the smallest ratio is 2 bariums to 1 silicon on that one. Rubidium nitride. Rubidium nitride, we got to get the symbol for rubidium, and the symbol for rubidium is Rb, and nitride is N. And so I'm going to go over here and I'm going to look on the periodic table, and rubidium is right here, plus 1. Nitride right here, minus 3. So I pull those charges off the periodic table, and I have a plus 1, and I have a minus 3. Sorry, my pen likes to connect things that it thinks I'm trying to draw here. Crisscross, the 1 goes behind the nitrogen, but you don't write the 1, and the 3 goes right behind the rubidium. And the formula then is Rb3n. And I should say, if you're doing these, I always like to clean them up. If I'm using pencil, I don't want to see the charges, or I rewrite it. And so the formulas without the charges on them are Ba2Si and Rb3n so far. We got good old barium iodide up next. And so barium symbol is Ba. I'm not going to use the periodic table now. If you got one yourself, you can look these up. Barium is a plus 2. I'm getting that from the periodic table. Iodine is a halogen, so it's a minus 1. And again, it wants to connect that for me because it doesn't think I know what I'm doing. So iodine minus 1. Crisscross, the 1 goes behind barium, and the I gets the 2, and so it's just BaI2. And I will go back in here and erase the charges to clean it up a little bit, make it look pretty. Okay, that's your basics right there on naming these. The next thing we'll take a look at here is what do we do with polyatomic ions. Polyatomic ions, bring this back over here. Talk about those. Here's a list of them. These are the ones that, if you're one of my students, you have to memorize these names and these formulas and these charges. And you see these polyatomic ions, which are just groups of atoms that occur so often. They've been given special name by chemists. So we have ammonium here, and we have acetate. And it's 2 different ways to write it. Cyanide, hydrogen carbonate, which is also known as bicarbonate. Hydrogen carbonate is the proper IUPAC name, but a lot of people in the United States I know still use bicarbonate. Hydroxide and nitrate and nitrite, and so you got this list here. And so we just have to know what these are, and we can use these names. Down here at the bottom in your notes I have some other ions that come up quite often. This is hydrogen sulfate, HSO4. S2O3 is, I think it's thiosulfate. And C7H5O2 with a -1 charge is benzoate. C6H4O7 is citrate. And Cr2O7 is dichromate. You've got a chromate on your list, CrO4. Dichromate is Cr2O7. Different charges on here, just ones that occur somewhat often to give some differences here in the problems that we're working, but I'm not going to have you memorize these because they don't occur that often in most of the work we do. Naming and writing formulas on these is the same idea that we did before. So all we have to do is incorporate the names of these ions now into how we name these things. So LiNO3, well, we know that Li is lithium. And we look up NO3. NO3 would be the nitrate. And of course, there is a reason why they're named eights and ites, but that goes beyond the scope of this right here, and I usually tell it to people when we do it. Na2SO4, we have sodium. And you look up SO4, you start to memorize it, and this is called sulfate. Ca3, C6H4O7 with a 2 in parentheses. This is calcium. And I believe this is the citrate ion. NH42SO3. We have ammonium. This is 2 polyatomic ions. This is ammonium. And SO3 is the polyatomic ion sulfite. And you make sure you know the difference. You now have a sulfide, which is just sulfur with a -2 charge. And you have a sulfate and you have a sulfite. Writing formulas is basically the same thing that we have done in the past. All you got to do is write your formulas and then do your crisscrossing. The only change here is when we write the subscripts, we need to put polyatomic ions in parentheses. And we'll show you how to do that here in just a little bit. I think I'm going to shrink down my writing tool here. So we're going to do ammonium chloride. So ammonium is NH4, and you either memorize or look up that this has a +1 charge. Chloride is a Cl, and it has a -1 charge, and so this is simply ammonium chloride. Sodium carbonate, so we know what sodium is, Na. We look up the charge, +1, and carbonate is CO3, and it has a -2 charge. Now we crisscross these. The 1 goes behind carbonate, and I don't have to do anything about that. And so the sodium gets a 2, and so the formula for sodium carbonate is Na2CO3. Barium phosphate. Barium is Ba. Looking on the periodic table, it has a +2 charge. Phosphate is PO4, polyatomic ion. It has a -3 charge. When we crisscross, the 3 goes over here behind barium. The 2 has to apply to the phosphates. I need 2 phosphates. And so when I crisscross, I wrap this in parentheses, and I put the 2 on the outside, telling them I need 2 negative charges. Now, if you go through here and do the total charges, I have 2 phosphates with a -3 charge, so the total charge is -6, and I know all of this has to add up to 0, and I have 3 bariums with a +2 charge, and barium, total charge of all the bariums is now a +6. +6 -6 adds up to a grand total of 0. Again, you don't have to think about it as long as you're doing the crisscrossing and the reducing at the very end, because the crisscrossing does that pretty much for you. Okay, that's why I like that particular method, but you got to understand you're balancing off charges too. We're going to use those concepts more when we do the not the polyatomic ions, but the transition metals here in a little bit. All right, back to my red pen. Aluminum acetate. Aluminum is Al. Formula for acetate, the one I'm going to use is C2H3O2 minus 1 charge. Now that's supposed to be a minus 1. 1. And aluminum is a positive 3 from the periodic table. When I crisscross, I got to wrap the acetate in parentheses. And I write that 3 on the outside. And the negative 1 over there. We crisscross to the aluminum. And it turns out we don't need to write anything on that one, because the 1 is already there. We don't have to write it. So the formula for aluminum acetate then is simply C2H3O2 in parentheses with a 3 on the outside. And I will clean up these. And there's my total formula without any of the charges there. All right, the last part is naming the transition metals tin and lead. So this applies to these things right here. And you just got to learn to recognize those transition metals and the tin and the lead. And if you see the names over here, you see we have some Roman numerals on here. So let's talk about how those operate. We're going to use something called the stock system, because transition metals, tin and lead, are what I call multivalent. They have multiple charges on them. And so the example I gave here is copper. There's a copper 2 and there's a copper 1. So you have to tell people what type of copper that you have. And if we go to the periodic table, these don't have the charges on them. But for instance, cadmium could be a +1 or a +2. Iron could be a +2 or a +3. Copper could be a +1 or a +2. Nickel is probably a +2 or a +3. So in the past, I told you your best guess is a +2 inside the transition metals, but that no longer applies. Now we have to be specific about what type of these elements there are. Tin can be a +2 or a +4. Lead can be a +2 or a +4 as well, and so we include tin and lead. Thallium also does that, but honestly, thallium doesn't come up enough. I'm not going to have you recognize that one. There's just not very many compounds with it in there. So the stock system uses Roman numerals to tell a person what type, what oxidation state of that metal we have here. So in this example, copper 2 sulfate is telling you that copper has a +2 charge, sulfate has a -2 charge, and so the formula for copper 2 sulfate is CuSO4. Copper 1 sulfate has a +1 charge. Sulfate still has a -2, so we still have to crisscross. And so if we crisscross these numbers, you'd get a 2, and sulfate would be still SO4. So copper 1 sulfate is Cu2SO4. Notice that the Roman numeral is not the subscript number. It's the charge on the metal. The two exceptions that I will let you know about, especially for my students, is that zinc and silver aren't multivalent. They don't have two oxidation states. Zinc is always a +2, and silver is always a +1. So you have something like silver nitrate. It's not called silver 1 nitrate because silver is always a +1, so it's just called simply silver nitrate. All right? Let's take a look at how to do this now with the transition metals and tin and lead. So, decoding. This gets a little bit hairier now because we got to tell a person what type of vanadium we have. So I know it's vanadium, and I know it's vanadium something, and so I'm going to leave myself a little space here, and I can do that easily with the keyboard. And CH3COO is the other form of acetate, so I know it is vanadium something acetate. So now all we have to do is figure out the something. I need to know what the charge is. And the way to do that is you got to work your way backwards, and we're going to have to just do some figuring out of some charges here. So let's break out the pen. Well, there's two ways to do this. And the first way I'm going to teach people to do this is the tried and true will always give you the right answer. There is a shortcut, but the shortcut sometimes fails. So we have V. We're going to start with the acetate. I know the charge of acetate is -1. There are 5 acetates. So 5 acetates with a -1 charge, all of the acetate adds up to a total charge of -5. And I know that all of the charge has to equal 0. This is not being kind to me here. So, equals 0. So this one atom of vanadium has to balance the -5, so it's not much of a logic leap to figure out that vanadium is a +5 charge. So if vanadium is a +5 charge, we're going to put the Roman numeral for 5 in parentheses, and that is a capital letter V. So this is vanadium 5 acetate. So the next one we have MnNO3 and so I start decoding, and I know Mn is manganese. I know it's something. So manganese something, and if you're writing it by hand, you'd of course leave more space than that, but I can type it in, so that's no problem. NO3 is nitrate. So it's manganese something nitrate, and now I have to figure out what the total charge of it is here on here. So we're going to go working backwards again, just like we did there before. So we're going to start with the nitrate end, and I know that nitrate is a -1. There are 3 of them, so -1 times 3 is a total charge of -3. I have 1 atom of manganese that has to balance that I know has 0 charge, and so manganese must be a +3 ion. +3 minus 3 equals 0, so this is manganese 3 nitrate, and so I type a manganese 3 in there. Done. Now here's where I'll tell you the trick, but you got to be careful with the trick. The trick is called the reverse crisscross. You ask yourself, how did we get these subscripts in the first place? Well, we got them from crisscrossing the charges. So what happens if we just did the reverse? Well, if we take our vanadium acetate here and we reverse crisscross the charges, we would put a 5 above vanadium and a 1 above acetate. Acetate's a -1 and vanadium's a +5. And we got vanadium as a +5. Here's how you know this works. If the right charge is above the anion, which in this case acetate is a -1, then the reverse crisscross works. We're going to see one here in a minute that doesn't work. So reverse crisscross works here. Reverse crisscross works here as well. This 3 on the outside would go above manganese. The invisible 1 would go above nitrate. I know nitrate is a -1 charge, so reverse crisscross works here, and this is manganese 3 nitrate. So if we do the same idea here to lead phosphate, I know this is lead something phosphate, and we try the reverse crisscross to this, what ends up happening? Well, I reverse crisscross this, and I put a -3 because it's the anion, so a 3 goes above here, and a +2 goes above lead. Is phosphate a -3 charge? Yes. Yes, it is. So then the reverse crisscross was okay. If my anion is the correct charge, reverse crisscross works. And some of you are probably asking, well, I thought that was a 2, and you're correct. That is definitely a 2, not a 3. Wrote a 2 by mistake. You reverse crisscross this 2, so that's really a +2. I was looking at the 3, confused myself there. So this is the 2 that reverse crisscross. This is a +2 above lead, and this is a -3 above phosphate. The phosphate is a -3 charge, so reverse crisscross does work in this one instance, and this is indeed lead to phosphate. Okay? Now, we could have always done the tried and true method on this of writing down our charges. Matter of fact, that's probably a good thing to do right here to show you what happens in this particular instance and how people could go wrong here and make a mistake. So let's do the standard way. We would start with phosphate, and we would write a -3, because phosphate's a -3. There are 2 of them, so -3 times 2 is a total charge from all the phosphate as a -6, and all of that has to add up to 0. So that means all of the lead has to add up to +6. Well, there's 3 atoms of lead, so I need to take this +6 charge and divide it amongst 3 lead atoms. 6 divided by 3, each lead atom has a +2 charge. So each lead is lead 2 phosphate. Okay? And that's how you would deal with it. We haven't seen one here with a number in front of it, but we could have reverse crisscrossed it, or we could have done it the old-fashioned way. Let's look at the reverse crisscross on this one. Cr2Si3. If I reverse crisscross this, chromium gets a +3 above it. The 2 goes above Si, so I'd write that as a -2. Silicon, however, we look up on the periodic table. Silicon is in this family right here. This should be a plus or -4. And we got a +2. I'm sorry, we got a -2. -2 isn't right for silicon. Reverse crisscross has failed us. That is not the correct answer. And the reason for that is because when we write the formulas, there's sometimes a reduction step to those. So this fails because the right charge didn't get above silicon. So now we're going to do the old-fashioned way. And there's also a way for the reverse crisscross people to fix that if they want to, but I'll show you that at the very end here. So let's just go ahead and do the naming first here, I guess. I know it's chromium. Something. Si would be silicide. So now I need to figure out what that something is. So we're going to do it the old-fashioned way because reverse crisscross does not work for us. And the old-fashioned way, we're going to start with silicon. It is written last, so I know that the charge is -4. -4 times 3. Silicon has a total charge of -12. I know it has to add up to 0. So that means all of the chromium has to add up to a +12. Pretty sloppy there, but you get the idea. But I have 2 chromium atoms, so I have to divide the +12 into 2 chromiums. 12 divided by 2. Each chromium atom is a +6. So this is chromium 6 silicide. And so we write the 6 in parentheses. And 6 in Roman numerals is Vi. Done. For those people that do the reverse crisscross and you had a 2 above silicon, a -2 above silicon, and a +3, well, since silicon's really is a -4 and you got a 2, you just simply double everything. And so if I multiply everything by 2, -2 times 2 is -4 for silicon, and that's right. And you multiply the 3 that you wrote above chromium, 3 times +2 is 6, and you get chromium 6. All right, so writing the names is now a little bit more difficult because we have to find out these charges. Doing the formulas, usually a little bit more simple. So we'll quickly go through these. I'll pick a color here in blue, thinner line here, hopefully a little bit more detail. Tin 4 oxide. No longer have to look at the periodic table for the elements because they're telling me I got tin. It tells me that it's a +4. And that's supposed to be a 4. Oxide, give myself some space, -2. I have a +4 and a -2. I crisscross, a 2 and a 4. But a 2 and a 4 are reducible. I'm going to try to write this so it doesn't try to close that gap for me. So I got a 2 and a 4. Those are reducible. So we're going to go ahead and rewrite that as Sn. Divide everything by 2. So 2 divided by 2 is 1. SnO2 is the correct formula for tin 4 oxide. We have iron 3 bicarbonate. So we have Fe +3 charge. So I write a +3 above iron. Bicarbonate is HCO3 and polyatomic ion with a -1 charge. And I'll try to write that so that the actual -1 goes in there. Again, it wants to assume that it knows what it's doing, and it does not. Crisscross, the 1 goes behind Fe, and the 3, I got to wrap my bicarbonate in parentheses and put a 3 on it. Fe, HCO3, 3, with the HCO3 in parentheses. Copper 1 thiosulfate, we have Cu. Thiosulfate is S2O3, I hope. Hope I got that remembered right. I'm going to have to go back here to my polyatomic ions. S2O3 with a -2 charge. So I've got S2O3 with a -2 charge. Copper's got a +1 charge, so +1. Crisscross, I don't have to write the thiosulfate in parentheses because the 1 is going behind it, so it's just S2O3. Lastly, we have nickel with a +3. Oops. So we have nickel, put a dot above it, with a +3. Chromate is CrO4 with a -2. So the 2 goes behind nickel. I have to wrap the chromate in parentheses, and the 3 gets written outside of it. CrO4, 3 in parentheses. And I'll try to make that 4 a little bit more readable there. There we go. And I'm going to go back through here now, and I'm going to get rid of the charges just to kind of clean this up a little bit. And so there's my FeHCO33 and my nickel chromate. All right, that's how you deal with polyatomic ions. I hope that helped people a little bit. I see I lost my Fe on here, so we'll quickly put that back on in blue ink. And so that was FeCO3 in parentheses 3. And it's bicarbonate, so there's an H there too. HCO3. All right, if you have any questions, you can email me if you're a student or leave me a message here on YouTube. Thank you very much.